Picking up on 402 and the ideal gas law. Okay, ideal gas law. We're given the formula PV equals nRT. Why don't I just ask you this? You've read it, you've outlined it. For some of you it was a page, for some of you it was a paragraph, for some of you it was this formula and a couple little words. In this section between 402 and the end of the chapter, like I said, there's 2 labs, there's example questions, there's very little content there. What did you pull out from this section? What is the significant portion that remains in this chapter, given the ideal gas law equation? If you were to say right now, these are the things that we need to make sure we remember, what would those be from your perspective? Get the ideal gas constant. Okay, so this is our R value right here, right? That's the ideal gas law constant. Do you know what each one of these variables represent? Okay, so it's pressure, volume, number of moles, ideal gas law constant, and temperature. Let me ask you a question again. What value, what units does pressure, volume, the amount, I guess you'd say, and the temperature, what units do they need to be in? Now, up until this point, we've said that pressure and volume, they could be in any units, like for Boyle's law, PV in the first state equals PV in the second state, right? We said that pressure and volume could be in any units because whatever units you have in the first state, as long as you use the same units in the second state or vice versa, the math will work. Okay, and then we said with Charles' law, the volume over temperature, okay, the same thing, but what did I recommend you always do with temperature? Even though it could be in any units, we recommend that you do what? Convert it to Kelvin, right? Use Kelvin, because we do the combined gas law then, you know, we get PV over T in the first state equals PV over T in the second state. We just encourage you to always use Kelvin as practice. Whenever you use temperature, and I misspoke there just a moment ago, but no, it has to be in Kelvin, because what happens when Kelvin gets too small? If we use Celsius and we approach the freezing point, what would happen? As we approach the freezing point of water, the temperature is moving from a number moving closer and closer to what tragic number for division? 0. And as we move towards 0, our answer becomes undefined. So when you use temperature, it always has to be in Kelvin. Okay. Pressure and volume, they can be in any units because they're not going to go through a 0 point. Temperature, we have to use Kelvin because it has a 0 point, but that 0 point is an absolute 0. Okay, negative 273.15 Celsius. It's so far down there, we're not going to encounter that in normal operations. That's where, remember, when it blows up at 0, that's when we talked about the hypothetical, the philosophical ideas of matter having no volume, takes up no space, there's no motion, time stops, all that kind of stuff. That blow-up point is outside of our ability to reach when we use Kelvin. If we use Celsius or Fahrenheit, that blow-up point would happen within our normal operating sphere. So 0 degrees, the true 0 degrees is way down there. Well, with pressure too. Remember with 760 millimeters of mercury, 760 torr, 101.3 kilopascals, and 1 atmosphere, the 0 point is still the 0 point on all of them. They all have an absolute 0 for pressure. There's no arbitrary middle point that's 0 pressure. 0 is 0 for all 4 scales. With temperature, you've got arbitrary 0 points, unless you use Kelvin, which has an absolute 0 point. So temperature has to be in Kelvin, but in this formula here, what units you have for pressure, volume, and temperature are going to be based upon the R value. Now in the text here, they gave you 0.0821 and the units were liter atmospheres per mole kelvins. Okay. So Given that 0.0821 liter atmospheres per mole Kelvin, what do you think the units of pressure have to be? Atmospheres. Volume has to be in liters. Obviously moles, that's the amount we have. Temperature has to be in Kelvin. There is a different R value in different scales. Matter of fact, in paragraph in 403, it mentions that. I think that's where it is. For example, they give you 8.315 Pascal meters cubed per mole kelvins. The R value there is 8.315 if you use those units. So you can have different R values, but the R value, the constant value, is going to give you the units that you need to use for your equation. So again, because the R value here uses liter atmospheres, my pressures have to be in atmospheres, my volumes have to be in liters, and I'm computing for moles, and temperature has to be in Kelvin so that the units will cancel each other out. Now, as we said before, that the characteristics of the gas are not based using pressures and temperatures, all these different in the gas phase. The characteristics of the gas unique to the gas is not the primary thing. The primary thing is how much of that gas you have in moles, or how many different molecules or different atoms you have is the key point. And for the PV equals nRT, the ideal gas law, we're solving for the number of moles. Now, the section that comes next is using the gas law in stoichiometry. What is stoichiometry? Let's go back several modules. What is stoichiometry? Just a very basic understanding, very basic definition of stoichiometry. I know you're used to. I don't like the silence, so I only wait so long and then I fill in the silence. So I'm using a teaching technique called making you uncomfortable by the silence. Ma'am? So you're relating quantities. What are those quantities? How do we relate those quantities? What's the units we use? Moles, right? Rating moles to moles. So when you have a balanced reaction equation, given a balanced reaction equation relating the number of moles of one reactant or product to every other reactant or product. Remember, we have a balanced reaction equation, and then we're given a certain amount to react with excess of the other reactants. We can compute how much product we're going to produce, relating moles to moles. Now, using PV equals nRT, we have a way of computing how many moles are in play. You can see if we rearrange PV equals nRT, our ideal gas law, the number of moles I'll go through a lot of markers. Excuse me. If we take the ideal gas law, PV equals nRT, and rearrange it, we have N equals PV over RT. Okay, see that? Basic algebra. I'm rearranging the formula to solve for N. N is going to be PV, RT slides underneath. PV over RT is going to be my number of moles. So if I have a pressure and a volume, and I have the right ideal gas law constant, and I know the temperature, I can compute how many moles are in play. And if I know the reaction that produced that number of moles, guess what I can do? I can use stoichiometry given pressure, volume, and temperature of a process. And we need to see that. We'll do a couple examples here to show you that. Let's take a step back, though, and just use the ideal gas law in example 11.5. It's page 405. A gas is in a 12.2 liter container. So it's a gas, so we use gas law, is in a container that has a certain volume of 12.2 liters. So my volume is 12.2 liters. And a pressure of 1.02 atmospheres, 1.05, excuse me, 1.05 atmospheres. And a temperature of 25 degrees Celsius. How many moles of gas are there? Okay. Well, as we wrote on the board just a moment ago, using PV equals nRT, the ideal gas law, I can rearrange that to solve for N, the number of moles. N is equal to PV over RT. Now, the value of R that I have using 0.0821 is in liter, atmospheres, and Kelvin, right? Temperature here is in Celsius. I've got to have it in Kelvin to do this. So I'm going to add 273, 1.5 is 298. And it's at the ones place, so I'm going to leave it at 298 Kelvin. .05. So pressure, P, volume, 12.2 over R, T. Okay, those are the actual values. Let's take a look at the, maybe be helpful. Let's take a look at the units. This is the math portion, right? This is the, we're going to actually compute the number. Let's check the units. It's 1.05. What are my units there? 1.05 watts. Atmospheres. Okay. So for this right here, I've got atmospheres times 12.2 is liters divided by my R. What's my R again? The R value? What's the units? It's right on top there again on 403. Liter atmospheres, mole kelvins. Okay, that's my R. My temperature is in Kelvin. Okay. So if I had more space across here, I would put the units all to the right beside it. So this is going to compute my number. This is going to compute my units. It's atmospheres times liters divided by R, which is liter atmospheres per mole kelvins times kelvins. Now let's just address canceling the units. Atmospheres cancels atmospheres, liters cancels liters, kelvins cancels kelvins. And my final is a 1 over 1 over mole. See that? These all become ones, and all I'm left with is a 1 over 1 over mole, which is the same as 1 times moles over 1, which equals moles. So I'm solving for moles. My N. And you can see on top of 405 that this math comes out to be 0.524. 0.524 what? Moles. So they only give you one example of how to do this, because once you get over the shock of PV equals nRT, making sure you have R in the right units for R, meaning you need the right values for P, V, N, and T. It's just plug in the numbers you're given to compute the number of moles. Bottom of 405, they move into this idea of using that number in stoichiometry. So let's flip over to 11.6 on page 408 and walk through example 11.6, at least the first part. Okay. You're given a balanced reaction equation of 2 hydrochloric. This is aqueous. I'm going to drop I'm going to drop the phase symbols right now. 2-hydrochloric aqueous, so it's in a solution, plus zinc solid. So you've got hydrochloric acid in a solution. It's diluted, it's aqueous, so it's the diluted hydrochloric acid, and you're going to shake solid zinc into it. That's what's happening here. The aqueous and the solid. Solid zinc is going into the hydrochloric acid, and it's producing hydrogen gas and zinc chloride. Okay, so as you're taking the hydrochloric acid and you're shaking the zinc into it, hydrogen gas is coming out of the beaker, and you've got zinc chloride is going to be the salt that's dissolved in the solution. Okay. And it says if 512 grams of hydrochloric acid if 512 grams of hydrochloric acid are reacted with excess zinc, at a temperature of 24 degrees Celsius and a pressure of 0.95 atmospheres, what is the volume of the gas that will be produced? Okay. The volume of the gas is going to be hydrogen, right? It's the only gas being produced. So I'm going to be relating. All happy to see that again, aren't you? So what would be the volume produced? Well, first, the clue is that we're using the ideal gas law, PV equals nRT. That's going to give us a way, given certain pressures, temperatures, to relate a volume by how much is there. How many moles? How much? So first thing we have to do is compute how many moles of hydrogen gas are being produced. And then, given how many moles are produced, we can compute the volume of that gas produced. So this first part should be pretty straightforward. How am I going to go from mass? I need to figure out moles, right? This block right here is my mole block in the solution pathway. This is a mole block in my solution pathway. Okay. And I'm going from mass to moles. So I'm trying to end up here. I don't need to go to mass. I don't need to go down here to concentration. I end at moles. So I have a certain number of mass, but I need to come up with a number of moles. How am I going to do that? The operation is division by what? Molar mass. The molar mass of what? Hydrochloric acid. Molar mass of hydrochloric acid, the book gives me 36.5. Should give you too, right on the example 11.6. So 36.5 grams per mole. When I divide grams by grams per mole, it gives me moles. The book here says it's 14. So using our solution pathway, I can see 14 moles of hydrochloric acid is the same as 512 grams of hydrochloric acid, because every mole is 36.5 grams. Okay. So again, this is from both 1, 2, and 3 chapters ago, this stuff. Mass per mole gives me moles. I need to figure out how many moles of gas are produced. How do I move across this line? My stoichiometric coefficients, right? I got to look at the relationship. It's a 2 to 1. See that? 2 to 1, the implied 1. Since I'm moving from left to right, moving in this direction, my multiple becomes 1/2. The 2 is driven below times 1/2. So 14 times 1/2 is equal to 7. 7.0. I've got 7.0 moles that have been produced. I'm done with that part because all I was trying to compute was how many moles. Why? Because using the ideal gas law here, PV equals nRT, I've been given pressure, I've been given temperature, I know R, I've been asked for this, and I needed that. That's my N right there. 7.0 is the N for my number of moles to use the ideal gas law. So let's do it. Solving for V, I've got PV equals nRT. I've been asked for the volume, so I rearrange for volume. V equals nRT all over P. Plug in the numbers. Making sure that my units are atmospheres, liters, moles, degree Kelvin. So the N value here, 7.0 moles. R, 0.0821, and I'm going to drop all the units. We've already done that once, okay? But using 0.0821, make sure that it's in liters, atmospheres, moles, kelvins. Temperature. Can I use that temperature? I need to convert it to Kelvin, right? So 273 makes it 297. And my pressure was 0.95. Check my math real quick. Okay. Tells me that I'm going to come up with 180. Now what we've just done is taken standard stoichiometry and added one more level of sophistication to it, one more alternate way of expressing it. Here's what it says. If I have a balanced reaction equation of 2 hydrochloric plus 1 zinc produces 2, or 1 mole of H2 gas and 1 mole of zinc chloride, salt, in the water, then if I have 512 grams of hydrochloric acid and excess zinc, it will produce 7 moles of hydrogen gas, which, when I collect those 7 moles, given that the temperature is 24 degrees Celsius at 0.95 atmospheres, it will fill a volume of 180 liters. It's kind of like, let's think this through together. I haven't done this yet. Well, let's think of a possible way of changing our solution diagram. You can help the future classes because this is all brainstorming now, okay? You can participate too, Austin. Brainstorming. Hey. Never mind. No scarecrow jokes. Here we go. Sell tickets to Wizard of Oz. Okay. Thank you. Let's think about this. The big H. Okay? We said before up here is mass, molar mass, moles, concentration, and volumes, right? And everything else on the other side is the same, right? So moving from moles for the ideal gas law, if we're going to end with moles, So if we were solving for moles, we're given something, something divided by something gives us that. And something times something gives us that. Here we've got something times something divided by something times something to give us this. So we need to somehow get into moles using the same Molar Bridge type analogy. That's what this is called, the Molar Bridge. How are we going to move from certain units to other units? I know there are other classes that have done this, but let's think about it. If we've got something and we want to make it, if we've got P times V and we're moving towards moles, we would need to divide by RT. See? And the way we've done it so far in class here has been down is division, right? So the way we've been doing it, it might be something like this. PV RT. Okay. Trying to come up with an aid that'll help you. I'm modifying our diagram. So if I know my pressure and my volume, and I know my temperature, if I'm given pressure times volume, and I divide it by temperature, which is why I'm kind of moving downward, if I take this divided by this, it'll produce how many moles I have. Okay? If I have the number of moles, and I multiply it by RT, it'll give me PV. I haven't done this with another class this way yet, so let's just think about that. Will that work? As long as we're in the right units. Just kind of adding this to the graphical diagram. Ways to get moles. How do we get moles in a balanced reaction equation? Given the mass, I divide by the molar mass, I get moles. Given a volume, multiply it by the concentration, I get moles. Given the pressure and the volume, divide it by the correct R value, which will generally be 0.0821, which means it's got to be atmospheres and liters, divided by R times T, that'll give me moles. Given moles, multiplying by RT will give me PV. So that'll work. In the same way on this, yeah. Okay. See, my fear would be, rather than doing something like this, it's basically the same thing, right? Whereas it's mass divided by molar mass, it's PV divided by RT. If you can visualize it better by being at slant angle like that, that's fine. But what do these drive to? This divided by this gives us moles. Mass divided by molar mass gives us moles. Volume times concentration gives us moles. In stoichiometry, it's all about the moles. We need to get it into moles in some way. So if we're talking about a gas, this is the only way we can use PV and RT is with gases. With masses, it'll actually work for any state, won't it? I have the mass of the gas as opposed to the volume of the gas and the pressure of the gas at a given temperature to get the number of moles. Let's go ahead and see there's another part to this, another half on page 409 of example 11.6. Let's see if we can use this kind of a solution diagram to solve it. So the water and the hydrogen are gases. magnesium solid, magnesium hydroxides, listed as a solid. Okay. If 4.5 liters of water vapor if 4.5 liters of water vapor at 200 degrees Celsius and 4.94 atmospheres are passed over excess magnesium how many grams of magnesium hydroxide will be produced? This is a gas, so I'm going to put it over here, the gas volume. So 4.5 liters, yeah. Okay. We're given, related to the water vapor, we're finding mass relative to the magnesium hydroxide. We need to go from moles to moles. Stoichiometrically, it's a 2 to 1. We're going in this direction, so my multiple is going to be 1/2. Okay. How many moles of water are in play? Well, we could have mass divided by the molar mass to give us moles. We don't have the mass here, do we? So we're going to be coming down with PV RT to give us the number of moles. Is everybody okay with this imagery, this solution pathway? The math you're doing is PV divided by RT equals N. It comes from PV equals nRT, rearranged N equals PV over RT. PV divided by RT is going to give me the number of moles. I need to get it in moles. So PV, because my R is in liters, atmospheres, moles, degrees Kelvin, those have to be the units. So PV is going to be 4.94 atmospheres. That's my P. The V is 4.50. That's this first part, P times V. Divide all of that by R times T. T has to be in Kelvin. It's given to me in Celsius. So what is my temperature here in Kelvin? .473. Good. So 473 K. That's how many moles I have. PV divided by RT. Book for my cheat gives me 0.572 moles. 0.572 moles. Okay? So moving across, multiplying that by 1/2. See, I've got this blocks now. Now I'm just back into my standard stoichiometric solution. Given the pressure and the volume and temperature, and knowing the constant, I can solve for how many moles are in play, and then how many moles are produced. Well, if 0.572 moles are in play in the reaction side, my stoichiometry tells me that 0.286 moles are produced, right? I've got moles here, but I've been asked for mass, so I have to move in this direction. I have to move up. My process then is multiplication, and what am I multiplying by? To go from moles to mass, I multiply by the molar mass. Remember, down is division, or excuse me, down is division, up is multiplication. The bridge is molar mass, so I multiply by the molar mass. 0.286 times the molar mass of magnesium hydroxide. book cheat says it's 58.3 grams per mole. So if I produce 0.286 moles, and each mole is 58.3 grams per mole, I have produced 16.7 grams of magnesium hydroxide. Okay. So the big deal, or the big learn on this section is this. Given a pressure, temperature, and a volume, I can compute the number of moles in play using the ideal gas law equation of PV equals nRT. Solving for N, it's PV divided by RT, which will give me the number of moles. Using stoichiometry, that's so painful. Don't snap your neck, man. Come on. So as you're moving from here to here, this many moles in play produce this many moles based on stoichiometry. And then from there, hey, from here, I could be asked how many grams. What else could I be asked? Oh, at the same parameters, what kind of a volume, right? How much space would that take up? What would that look like? Well, again, you'd have to come back with PV equals nRT solving for V, which would be nRT divided by P to solve for V, to compute what the volume of that 16.7 grams would be. But it's all going to be some rearrangement of the PV equals nRT. Okay. So the PV equals nRT, the purpose there is to be able, for use in stoichiometry, is to be able to, for you to be able to compute the number of moles given the pressure, the volume, and the temperature, to compute how many moles are in play. And then relate it to some other reactant or product, so that you compute the consequences of that reaction, how much will be produced or how much was needed to produce that much. Given the time we have, let's go ahead and try, I'll give you a head start. Let's go ahead and just start working on your own 11.9. Go ahead and try to apply it yourself. Start working ahead, 11.9. I'll wait a few minutes and then I'll join you. On your own, 11.9. We've got octane, is burned to make gaseous carbon dioxide and water. Okay. It's burned, combustion. Combustion requires oxygen to produce carbon dioxide and water. What's the first thing you got to ask? I pulled this. This right here just represents the statement, octane is burned to make gaseous carbon dioxide and water. So I have the products of reaction, I have the reactants. What is not true about this yet? You have to ask yourself, is it balanced? Is this balanced? I know that octane and oxygen react to produce carbon dioxide and water. It's not, is it? So how many carbons do I have over here on this side? I have 8. Carbon only occurs here, and how many do I need to have? I need to have 8, right? If there are 8 over here, I need to have 8 over here. So the first step in balancing it would be to put an 8 in front of it. 8 carbons, 8 carbons. 18 hydrogens. I need 18 hydrogens. 2 oxygens. Here I've got 16 plus 9 is 25. So I need 25 on this side. How do I get 25 out of sets of 2? 12 and a half, right? 12 and a half times 2 is 25. Can I have a fractional coefficient? How do I get rid of it? Multiply by the denominator, the whole thing.
2C8H18 plus 25O2 produces 16CO2 plus 18H2O.
Now I can use stoichiometry. And again, that step should be old, familiar to you. How to balance the reaction equation. So mass, moving down, mass divided by the molar mass at 114.2 grams per mole for octane gives me 28 moles of octane. 28 moles in the balanced reaction equation relates to 2.2 times 10 to the second moles of CO2 gas. Because you multiply it, its relationship is 2 to 16, means I have a multiple of 8. 8 times 28 is 220. 220 moles of carbon dioxide gas at 1 atmosphere and 453 degrees Kelvin. Rearranging, what would be the volume of that? I'm rearranging this for volume. My N, that's the 2.2 times 10 to the second. My R is standard, my temperature, 453, divided by the pressure, it's at 1 atmosphere. So 8.2 times 10 to the third liters. 8,200 liters. Think about that for a second. Think about the scale. This is 1 gallon of octane. When it burns, produces 8,200 liters of carbon dioxide gas. That's huge. The volume relationship. 1 gallon of the liquid burns to produce 8,200 liters of carbon dioxide gas. And the difference is due to the, think about the phase. Liquid, they're all close together. They burn, become gas, they're separate. That volume, that space it takes up. So it's not like you take a gallon's, that's a volume, right? A gallon of gas, and when you burn it, you get a gallon of carbon dioxide. In this case, you take a gallon of octane, and it produces 8,200 liters of carbon dioxide.